Hello and welcome to the APL quest. See APL Wiki for details. Today's quest is the second from the 2016 round of the APL problem solving competition. We are given some numbers, normally as a list, but it could also just be a single number, and we are to compute the median. That is the middle element if you order them by size. And if there isn't any middle element, then we take the two middle ones and take the average of those. First, let's start with some test data. So there's a difference here between even and odd length lists because of there being a middle element or no middle element. So the first example we're going to do is we're going to have an odd number of elements. And here, if you order them, we get 1, 1, 3, 4, 5. And so the middle element would be the 3. Then, in this case, there is no middle element because we have 4 elements. So if you order them, 1, 1, 3, 4, the two middle elements would be one of the ones, doesn't matter, and a 3. And then the average of that would be 2. Then we could also be given a single element, in which case we're supposed to just return that. So this is not a vector, not a list. And we could also be given an empty vector, and the problem specification then says that in that case we should say that the median is 0, even though there isn't any elements. So the empty vector, empty list, numeric one, is written like this in APL. And finally, we should also make sure that we handle the one element case, because that's not empty, and there is a middle element, but you can't just go and take two elements because there aren't two, there's only one. And in order to get a one element list, we take a number and then we ravel it. So this flattens it out to be a list of all its elements, which is just that one. So this magnetic comma is called ravel. And then also note that APL denotes negative numbers with a high minus, and normal minus is for subtraction. And this removes any ambiguity. So now we have this list of lists, and we're going to try out our code on each of them. So what we're going to do eventually is we're going to use the each operator. If we use that to the immediate right of a function, it will be applied to each element, basically a map. Right, so how are we going to compute the median? There are a few different ways, and one way we could do it is to sort. And then we can remove the elements that are before the middle ones and the one that's after the middle ones. So let's just get started. So we define a function in the braces, and we're doing the each here. On this applies the function to each element, so that we're trying out all the different test cases. And then the argument inside the braces is denoted with the Greek letter omega. It's because the argument is on the right, and omega is the rightmost letter in the Greek alphabet. And so the way we sort in APL, there's no direct sort function in most dialects of APL, but what we do have is something called the grade. So this is the grade function. And what the grade does, so here's a problem. Our first problem is it won't grade our arguments because one of them is a scalar. It's a single element, and it doesn't have an ordering, so we cannot change the order. We cannot grade it either. And so much like we did when we were to write a one element list, we used the comma function, the ravel. We can do that here. So we could do a ravel on each, and then we can apply our function here, grade on each, and this will work. However, we can also combine these simply by parenthesizing them. And so this is called an atop. It's a sequence of two functions. And we only need parentheses here because we are calling it in in place, and we want the each to apply to both of them together. So we're grouping them with a parenthesis, and what this just means is apply the first function, that the one that's on the right, and then on the result of that, apply the second function. So now we can try this, and that works as well. So this is grade. What grade means is it gives us the list of indices that would put the array into order. So if we have a look here, the first one, 3, 1, 4, 1, 5. So then if we want the smallest element, then we need to go to position 2. That would be a 1. And the next one, because it's a stable sort, which means that if things are equal, then they preserve their relative ordering from how they came. So the leftmost one becomes the first one, and then the second one, which is in position 4, becomes the second one. And then we want element number 1, which is a 3, then element number 3, which is a 4, and then finally element 5, which is a 5 as well. And so too here. And that means if we take these indices and use them to index into the original array, that will be a sort. And APL allows multiple indexing in one go, so we don't need to map over the indices and then index. Rather, we can just take all the indices that we want and put them into the square bracket for the indexing, and that gets us those elements here. So now we get the sorted list representation of these arguments. We should also note here that what we're seeing is a 0 here for the empty list, but these arrows indicate axes that are available. So there's one axis in each, it's a one-dimensional array, and this circled bar thing indicates that there is an axis, but it's an empty axis, and the 0 is only here to indicate what type of array it is, so it's a numeric array. Okay, so now we've got the sorted list, and what we could do then is we know that the first and the last element are not the ones we are looking for. We want the middle elements. So we could drop the first element, so this is 1 drop, and we could drop the last element, so -1 drop means drop from the rear. Of course, this isn't entirely correct for our very short arguments over here, but we'll fix that in a moment. And we could keep dropping until we have 1 or 2 elements left. So we can see here we have 3 elements left, so we could do this again, 1 drop, -1 drop, and then we have the 3, which would be the median, and over here when we got 2 elements left, then we want to average the 2. So all we need to do really is keep dropping from the front and from the rear until we have 1 or 2 elements, and then that gives us our result. And we can do that in a recursive function. But before we start with the recursion, let's just set up our stop condition. Otherwise, we might end up going forever by mistake. And so our stop condition is, and this is, we separate the two statements here with a diamond, because diamonds are unbreakable. And then the colon here is a conditional. And so we have a condition on the left, and then the immediate result on the right of the colon. And if the condition isn't fulfilled, then we continue after the diamond with the next statement, which would be this. And so here we're going to take the tally of the right argument of omega, and this looks like a tally mark. So this is counting how many elements there are. And then we say if that is if 2 is greater than or equal to the tally, that means we have 0 or 1 or 2 elements, then we're done. We don't want to remove anything more. So then we could return the argument as it is. Now if we try this, we can see that we're preserving, now we didn't drop anything from these last cases because they already have 2 or less elements. Of course, we're not quite done yet. And if we keep dropping, we can try this. 1 drop, -1 drop here, then you can see that that only happens on the long arguments. But we don't want to do that. We only want to do one step. And then we have either 0 elements left, or 1 element, or 2 elements left eventually, once we do our recursion, and we'll take it from there in a moment. So how do we recurse? Well, it's very simple. We use this upside down triangle, which is actually upside down Greek letter delta, or del, which is like, it's called del or nabla, and it's kind of like a D. D stands for definition, so it kind of calls its own definition. And this allows us to recurse in an anonymous function, anonymous lambda, which is what we have here. So here we recurse until we have the length less than or equal to 2. And that is what we get here. So here we can see then we had the odd length, we're getting just the middle element, and we're done. If we have even length, we end up having 2 elements left. And if we, and otherwise, if we started short, we're just returning the other way. So now we want to compute the average of these. And there are a couple of ways we could do this. But there's a problem with the empty list for computing averages. So a really neat way, I think, is to do a cyclic reshape of this. We know that we only have 0 or 1 or 2 elements. And if we do this is a Greek letter rho, which is like an R, stands for reshape. So this reshapes to length 2. And it does so cyclically, which means that if we have 1 element, it becomes 2. If we have 2 elements, it stays as it is. If we have no elements, then it will use that type. Remember, this indicates the type, which is a 0. That's a prototypical number. And we will use that instead of any data, because there isn't any data there. So here we can see that we end up always with 2 element lists or vectors. And then it's very easy to compute the average of that. We can sum them. So this is a plus reduction. And then we can divide by 2 to get us our result. So these are the medians for all of our arguments. I don't particularly like parentheses, but we need a parenthesis over here because APL goes from has a long right scope. If only we had a division function that had swapped arguments, so instead of dividing the left argument by the right argument, you would divide the right argument by the left argument, then we could avoid this parenthesis. And while we don't have that built in, we can construct that using the commute operator or swap operator. So this takes the division and flips the arguments. So now the 2 goes on the left, and I like the way it looks like this. So we can assign this. So this is the recursive version of median. Okay, let's do it a different way. This is not a very good way because, of course, we're looping over or recursing here over and over and over again. Even though we have tail recursion, tail call optimization, still this is a bit silly to loop through like this and just peel off elements. Instead, we had this one drop, a negative one drop, and we don't have to use 1, we could use any number. So if we can compute how many elements we need to remove, that would be much better. And turns out, of course, we can compute that. So if we look at the number of elements, let's have a look at our original D here. So here we have length 5, and we need to remove 2 from the beginning, 2 from the end. If it had 6, there would be 2 middle elements, and we also needed to have 2 elements from the beginning and 2 from the end. Then 4, we need to remove only 1. And if we had 3, we also need to only remove 1, and then we'd end up with a single element in the middle. Then if we have 2 elements or less, we don't need to remove any elements at all. So clearly, this is something that has something to do with the length, but flattened down, so to say, to by half. So we have, if we start making our lengths longer, it will be 0, 0, 1, 1, 2, 2, 3, 3, and so on. And we can compute that, we can try it. So if we start by generating all the indices, so this is the index generator, Greek iota, iota is like an I for index generator. Then we can divide by 2. And we can kind of see it here, how if we round it off, we would get 2 of each. But we are a little bit off because this was this is 1 and 2 and 3, and really what we need to do here is drop less than that. So if we add -1, so you can see a case where the high minus does us good. Now for 1 and 2 we want to drop 0. For 3 and 4 we want to drop 1. For 5 and 6 we need to drop 2, and so on. And that's exactly the formula that we want. So and we're going to use the length of the argument, and then and this is yeah, should be obvious from before. This is round down floor. And then we this is the amount that we want to drop. So we computed that. We are assigning that to D. Next statement, we're going to use D in much the same way as before. So we're taking and sorting first, and then we can do a D drop and also a negated D drop. So this drops the first and the last. So we can try this on our arguments. Notice here the scoping. So even though our test data is called D, we can use the D inside, and there's no problem because inside we're using omega for the as a name. That's a special name for the argument. Oh, again we have the same problem that we're trying to do this on a scalar. So let's do the same trick as before. And this works very well. We can see that we get either 1 or 2 elements, which means we are almost done. We just need to do the same thing as we did before. We can do a cyclic reshape to size 2, and then we sum that and divide by 2. This gives us our median. So this was the median computed by dropping, computing the amount that we need to drop. But in fact, we don't need to modify the data at all by dropping elements. And what we could do instead is compute the elements that we want, the indices of the elements that we want. And then we can just go and pick those out directly instead of having to chop our way until we get to them. So how would we do this? This time, let's make sure to remember to ravel first. Okay, so let's think about it here. If we have length 3, we want element number 2. If we have length 4, then we want element number 2 and 3. And if we have 5 elements, we want element number 3. So it keeps going up and down like this. In fact, if we're going to sum them and divide by 2, we probably want them twice. So if we have 3 elements, we want element number 2 and then element number 2. If we have 4 elements, we want element number 2 and number 3. And so again, it's going to be this kind of increase by half all the time. Let's start off by the length. And instead of adding or subtracting 1 as we did before, we're going to add 0 and 1. And so this list is being added to the single number, which is the length. And then we divide by 2, and then we can almost see where we're getting at. Remember, the first one has 5 elements, and we wanted element number 3, and here we want this is with 4 elements, so we want element number 2 and number 3, and we can see we can just need to round that up, just like we did the floor before. The corresponding symbol going up, that is the ceiling. And so these are the indices that we want. Except for our short, too short thing, when the length is 0, then it isn't working right. In that case, we should just return 0 because we can't get the indices in of index number 0, index number 1. That doesn't work. So a couple of different ways we could do this. We could do it as before. We could say if 1 is, well, actually we only need to do it for that one element. So if 0 is, sorry, for that 0 element length, if 0 equals the tally of the argument, then we return 0. And then we need to use these indices. So this is, then we're done. That's our result. Over here, we need to use these indices to index into our argument. So we use the indexing, and then we just need to sum and divide by 2. Ooh, something isn't right here. Oh, of course. Yes. Do you spot what I've missed? We're indexing the um, into the original data that hasn't been sorted yet. So we need to sort that first, of course. So we use the grade just directly and index, and so this is the sorted argument, and then we're indexing into that to get our result. So this gives us our result. In fact, we don't need to check the length at all. We could just compare to the empty list itself. So if the argument is identical to the empty numeric list, then we return a 0. So that's another way that we could write this. And so this is the median using indices. And that's 3 ways of computing the median. There are a lot of different ways that it could be done. I'm not going to go through any more now. I'd like to mention a variant of this. So far, we've been sorting the numbers, and then we've been either peeling off from the outside, or we have been dropping from the beginning or from the end, and finally we've indexed directly into the sorted list. A different approach, a little bit, in getting the right elements out, since we're computing the grade, would be to index into the grade itself, and then use that to index into the main data. So let's modify this this median I just a slight little bit. And the reason for that is because when we're sorting here, it could be that we have a data type that's inefficient compared to indices. For example, floats that use up multiple bytes per element, whereas the indices themselves, at least for a small array, would just be 1 byte per element, or maybe 2 bytes per element. And so what we could do here is we could index into the grade, and then that gives us the indices that we need to get from our full argument, like this. So we can say median I2 on each of the data, and that gives us our correct result as well. Similarly, for the other 2 solutions, we could do something like this. Right, that's all for today. Thank you for watching.